So I believe that we left off on kinetics and thermal stability, right? Thermodynamic stability. Okay. So the way that we determine if something is going to be kinetically stable is by looking at the delta G, that activation, right? So if that activation gives free energy is large, then the reactant is going to be considered to be kinetically stable because the reaction because it reacts slowly. If it's small, then it's unstable. Then that means that we're going to have a fast reaction. So that kind of makes sense, right? So we look at like how acids separate, right? You know, if it's a strong acid, it dissociates almost instantaneously, right? It's a fast reaction because them being together is unstable, right? So they're looking to be separated, right? Where a weak acid, right? They stick together for a long time, right? So then that's going to happen for them to separate. It's going to be a very, very slow process, right? So because the other guy is favored. Okay, so this also, in the case of thermodynamically stable, if our delta G is less than 0, then it's considered to be thermodynamically stable compared to the reactants. The products are thermodynamically stable compared to the reactants. If our delta G is greater than 0, then it's considered to be the products are considered to be thermodynamically unstable. Okay, so let's see. Okay, so you guys are familiar with the rate of reaction, right? You guys remember how to calculate the rate of reaction? Yes, no, maybe? You don't remember the rate of reaction, the integrals and all that? Yeah, those guys, yeah. Okay, so the rate of reaction is going to equal to the number of collisions per unit of time times the fraction of sufficient energy times the proper orientation. So in this case, we have to take in consideration orientation of the products that we're looking at. Okay, so an increase in concentration is going to affect our rate. An increase in temperature is going to affect our rate. If we have a catalyst, it's going to affect our rate. Okay, so we know because we've done thermodynamics already and everything like that. You're familiar with the fact that temperature will definitely increase that speed, and then also having more of your products readily available, it makes it easier to sit there and get the reaction driven. Okay, so you remember the rate is going to be proportional to the concentration. So then rate is going to equal the rate constant times the concentration. Okay, now this is for a simple reaction, of course. You guys remember that back in the day? And so let's see. The rate of the reaction of methyl chloride with hydroxide ion is linearly dependent on both the concentration of the methyl chloride and the concentration of the hydroxide ion. At 30 degrees, the constant is K. For the reaction is 1.0 times 10 to the minus 5, and that's moles or over moles per second. What is the rate? What is the reaction rate when the concentration is equal to 0.10 molar and the hydroxide ion is 0.10 molar? What is the first thing that we're going to want to do? Not give you the answer. So what did they say about the rate?
It's the constant times the concentration.
Okay. So we know that it's the constant times the concentration. So we know we have K. Sorry. Rate equals K times the concentration of CH3, sorry, H3, Cl. And what else? Because they tell us it's linear dependent. What does that mean?
Wouldn't you have to multiply by the hydroxide
That's right.
ion?
Because it's linear dependent on both of them, right? Linear, meaning that, because if you guys remember, when we were talking about rate constants, they could be exponential, right? So they could be to the second power, they could be to the third power. It's rare that they're in the third power, but they could be the second power, third power, they could be in fourth power, right? And so then it would be exponential too, right? So in this case, you're saying it's linear. So the rate is going to increase as this guy goes up, and the rate is going to increase to that guy goes up. So that means that these both are going to be to the first power. That would be linear, right? Does that make sense? And the way that we determine how it normally is done experimentally. You guys remember that? Back in 1B. Okay, you're being honest. Okay. So now that we know that the constant is, it's the same. Same thing. Yeah. It means the same thing. Same thing. Just this book likes to write it backwards. Yeah. Okay. So, and we have the constant, so we just plug everything in. So we have 1.0 times 10 to the minus 5. And that's molar 9-1, seconds minus 1, times 0.1 molar and 0. Can you repeat that, please? Yes, they're both the same. Yeah, this is the constant K. Yeah, and this is the concentration, which is 0.1 molar. 0.10 molar. Okay, so then we get our rate is going to equal 1.0 times 10 to the minus 7. And that's moles per second. Or molar per second, molarity per second. Okay. Okay. It says, if the concentration of methyl chloride is decreased to 0.010, what would be the effect on the rate?
Would it be decreased?
The rate is going to be decreased, right? Because you're dropping from 0.1 to 0.01, right? Okay. What would be the effect on the rate constant? Anyone? Look at the equation. What will be the effect on the rate constant? There's no effect. Okay, so the rate constant is going to be independent of the concentration, but the rate itself is going to be dependent on the concentration. Now, the rate constant is dependent on temperature. So, and you guys want to write that down. So if I ask you, so what would be the effects of temperature? So if I increase the temperature, it's going to change that rate constant to be a higher value, or it's going to be a faster rate, so that you'd end up with a faster rate. When the temperature increases. So reactions happen faster when we increase the temperature. That's right. Yes, because the constant K is dependent on temperature. Even though it's a constant, that it's not dependent on the concentration, but it's dependent on the temperature. Okay. And so that's why it's important that they say at a stable temperature. Otherwise, if the temperature is changing for the reaction, that's going to affect the rate constant. How many of you guys were here when I did the experiment with the glow sticks? I know you were because of the class, or maybe yeah. So that's a good example, right? So as we increase, the glow stick that was in the hot water glowed faster, brighter than the ones that were in the cold water and the one that was at room temperature water. And the one at cold water was really dim compared to room temperature because the reaction is going slower. The kinetics is. Okay. Questions, concerns? Kool-Aid. Okay, so this is Arrhenius' equation. So this here shows us that that rate constant is dependent on temperature. Okay. So the constant K is equal to A times the E to the, and this is the activation energy divided by RT. And I'm going to have to apologize for the next components of our reaction there because it screws everything up, the next equation. Save it. Okay, and A is going to be, it's going to be based upon the frequency and the orientation of collisions. So it's like a collision factor. Okay. So this is all screwed up, but this is supposed to be an equation going in both directions. So this is supposed to be this direction and that direction. Okay, so the rates is going to be equal to K, K1, the concentration of A, and that should be equal to K minus 1, the concentration of B. And so our equilibrium constant is going to be equal to the ratio of, K1 over K minus A, which is going to be equal to the concentration of B over A. So our equilibrium constant is going to be dependent on our rate constants. And that was one of the connections that I did make with you guys in 2A. 1A, 1B. that class? Okay. So now this is going to help us kind of understand. So there are going to be, you guys remember what rate limiting steps are? We talked about it about that much. Rate limiting steps. What do you think it means? Rate limiting steps. Limiting steps. Okay, steps that limit my rate. Okay, so when we look at a chemical reaction can be made up into multiple steps. How many guys cook? Cook. Okay, how many of you guys bake a cake? Okay, so let's say we're baking a birthday cake, right? And this birthday cake is going to have frosting on it, and it's going to have writing and flowers and all those beautiful things on it. Okay, now what would be the step that takes the longest? Baking the cake, frosting the cake, decorating the cake. What was that? We're not getting fancy. It's bare minimum, you know, writing and a couple of flowers. Yeah, that's baking, right? So would you agree? Everybody agree baking will be the step that takes the longest? Yeah, it's including, that's all part of baking, right? That's the baking part of it. So it's the cake mix, the putting it in the oven, waiting for it to bake, right? And then letting it cool off. All that is part of the baking. Okay. So the cooking or the baking of the cake is going to be considered a rate limiting step. It's the step that takes the most time, right? The equation is going to be based upon that step because it takes the most time. The other parts of it, the frosting of the cake, if you're a good froster, you just wipe it on there and you just kind of, you know, good to go. And then you throw some flowers on it in the corner, you're good to go. And if your handwriting is better than mine, it'll take you 5 minutes, you know, to sit there and put, you know, happy birthday, Jesse on it, you know. So that step is considered your rate limiting step. That's the one that kind of controls the reaction. It takes longer to do that than anything else, right? So you're looking at that rate alone, okay? So usually we're looking at the one that takes the longest part, and that's going to dictate how fast the reaction happens, right? Because you can't whip out 5 cakes in 15 minutes, can you? Because it takes about 2 hours to prep the batter, get your pan ready, get your oven ready, let it cool off before you can do anything else, right? So that dictates the steps, okay? So now that's going to be the same thing that happens in the case of an organic reaction or any reaction in general, right? You're going to have steps that are going to be more slower than others, okay? So often these steps kind of result in transitional states, and that's what we're getting seen. So here we're getting a transitional state, right? Where you have the double bond starting to be dissociated, right? The hydrogen is coming in and becoming attached to our tertiary carbon. Our secondary carbon. And then that is still attached to the bromine. Now, This here is considered a transition, right? It happens very fast compared to the overall reaction, okay? But it's still a transition. We're going from one state to the next state. Then we get the formation of this guy. This formation is our rate limiting step. Okay? It takes longer to do this part. Then this guy, the attraction of the bromine is a very quick step compared to that. So because we had that transitional state and that formation, this part takes a while. That's going to be our rate limiting step. This is going to be the part that takes a while for us to sit there and form. So this process of breaking this bond is called, just for the carbocation. People will say carbocation. Right? Breaking the double bond and the formation of the cation. It's carbocation. Basically adding a positive charge to that carbon. Okay, so this next step is a very fast step, because what happens here is that we have our partially positive. So then this guy attracts that partially negative and interacts since it's charged, and then they form another bond. Okay, that guy is fast compared to formation of this guy. Okay, so these are the steps, right? So the very first step, this here is our transitional state, right? So once we get to our transitional state, it comes down because the transitional state is unstable. And then we do carbocation. And then we'll say that take that carbocation, we have the transitional state, and then we'll end up with our products. Okay. So if we take a look at this, this guy is it has a huge free energy. Right? So what does a large delta H mean? Delta H double cross, I don't know what to call it, activation. What is this a large value for this? The delta G, not delta H. So it's thermostable. Okay. Are you sure? Not G naught. This is the Gibbs free energy for activation. It's kinetically stable. Okay. And then the transition from this guy, where we have a small delta G. Okay. Okay. So if we look at it, these are two steps. So this represents each step. So we have the very first step, which is the carbonation or carbocation or carbocation. And then we go from our carbocation to the formation of our product, right? So two steps. So if we looked at it together, clear this. That's our very first intermediate. Our first transitional state. This here would be our intermediate. This is what our intermediate is. And then this would be our final product. Okay. And you see the two humps. So when you see a reaction that have multiple humps, that suggests that is a multi-step reaction. Okay. So again, our rate limiting step is going to be the very first hump because it's the highest, right? So your rate limiting step has the transition state at the highest point of the reaction. Okay, catalysts. So catalysts basically are going to just lower that barrier. So let's say, for instance, we have to climb up this hill, right? So this would be the reaction normally without a catalyst. And if we were able to just go find a tunnel that went straight through the hill to get us to the other side, that would be like a catalyst. Okay, so a catalyst just basically lowers that energy barrier. So it lowers that delta G, that Gibbs free energy. So it's not as high. Okay. Yeah, to kind of push it. Yeah, so that activation is unstable. So it kind of pushes us faster to that reaction. Right. So a catalyst, it doesn't necessarily change the energy of the starting point of the reactants or the energy of the reactant points. Okay. So it speeds up the reaction. So at the end of the day, you're still going to the same point, right? That's what we were saying. So we start here, right? And we end here. It's just that middle part of how we get there. It's going to be different. Okay. So the energy where we're starting at and where we're ending at is going to be the same. It's just that transitional state. We're fucking with the transitional states. Okay. We're messing with the transitional states. Gotta watch my language, man. My girlfriend's son was watching one of my lectures. He's 8. Yeah. Bleep, bleep, bleep. It'll be bleep, 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 bleep. Or say NC 17 on it or something like that at the end. Okay, so enzymes are a good example of that. So most biological reactions are going to require a catalyst. Most biological catalysts are proteins that are called enzymes. That's what enzymes do. They speed up reactions, right? So a lot of the proteins in our body, it's not that they're performing that function. They're just speeding up a function that happens that would normally happen really slowly to happen fast. So like for instance, if we have sugar on our plate, right? Over time, as it's exposed to oxygen, it's going to get broken down by that oxygen over time. But the amount of time it takes forever, right? Now, if we put a little bit of lighter fluid and light it all up, right? It'll burn it just like that, right? We'll get tons and tons of carbon dioxide, we'll get tons of water, right? We'll be good to go, right? Where that little accelerant that we added in that match got it started real fast. Now, that would be a quote catalyst because we're helping that process on a little bit, right? So your body does it the same thing. It would take for it to happen naturally without anybody getting involved in it. It would take, we'll say years, hundreds of years before that sugar gets broken down and oxidized the way it's supposed to, right? It takes forever. Your body does it in minutes, seconds, microseconds, milliseconds. So your body does it in milliseconds. So it's so fast, right? You blink and we think about it, right? You breathe and it's already happened, right? Okay, so enzymes serves as catalysts in biological functions. And you're going to have your substrates and you're going to have your products. So the enzyme is going to basically play with the orientation of the substrates to allow the reaction to happen faster. That's essentially what happens. Okay, so here's an enzyme. This is the active site for that enzyme to bind. So that an enzyme binds its substrate, it gets it in the right position so that the reaction can occur, and then it helps induce that reaction. Okay, so this here just is basically the side chains that binds the enzymes of the substrate. So here's your substrate. This is going to be your enzyme that's going to be binding. And so you'll notice that you'll have interactions between the enzyme and the substrate itself. And that's what's being shown here. Most of these are hydrogen bonds, right? Sometimes there'll be hydrophobic regions where you have things that are hydrophobic that'll be able to interact. Usually those things are hidden, you know. So the side chains of enzymes, they can be hydrophobic. I mean, not hydrophobic, hydrogen bonds. They could be dipole interactions, or they could be dispersionary forces. You guys remember all of those? Hydrogen bonds, oxygen bonded to a hydrogen that's interacting with an oxygen over here, right? That would be a hydrogen bond, or nitrogen, or, you know, okay. Some enzymes, they're going to have side chains that are going to be acids or bases, and sometimes nucleophiles. That's going to help catalyze reactions. Okay, which of the following statements about catalyst is false? A, the catalyst decreases the activation energy of a reaction. B, catalyst does not change the energy of the reactant or the products. C, a catalyst increases the amount of product formed. D, a catalyst increases the rate of reaction. E, a catalyst is not consumed in the reaction.
C. Because of conservation of mass.
That's right. So we know that it has to be C because of the law of conservation, right? Okay, ready for chapter? Let's go ahead and take a 5-minute break or 10-minute break. You guys can go Mesa, go pee, do something. Then we'll come back here and we'll start talking about chapter 6. Okay, so we've already been sort of playing with the electrophilic addition reaction. Okay, and so it's just, again, it's going to be a generic case, and then we're going to go through it specifically. Right? So here, in this case, you guys remember the double bond is going to act on the hydrogen, which is going to cause the carbocation of one of the carbons. So then it gets a plus, the hydrogen gets added. Then we have the bromine that forms its ion. That ion then later on gets added to that positive charge. This part, again, is the slow part of the reaction, that carbocation, right? And this is going to be that intermediate that we formed, right? So again, the electrophile causes the hydrogen to attach to the carbon, breaking that double bond. Then forming the cation. Then the bromine then adds the electrons to that the carbon cation intermediate, and then you form, in this case, a bromide complex. Okay, first part of the reaction is slow, so any carbocation is going to be a slow process, right? But the addition of the nucleophile is going to be a faster process. Okay. Okay. So again, your pi bond is going to be broken by your nucleophile, or let me say, this is going to act as your nucleophile. It's going to interact with your electrophile, forming a cation, and then that cation is then going to be attacked by that nucleophile that's now going to be adding to the carbon, that other carbon. So you're going to end up with your Y and your Z being formed here. Okay. Again, so this is a generic form of that equation, right? So don't get bogged down by hydrogen bromide. doing it, because it could happen with hydrogen iodide. It also could actually happen with hydrogen chloride or fluoride. So it can happen in all those circumstances. Okay. So this is just showing you this could happen under those different circumstances where you have the addition of the hydrogen and the bromide. Okay. So what alkene should be used to synthesize 3-bromohexane? You said 3. Hexene. Okay. So 3-hexene. Okay, anything else? That will look like 1, 2, 4, 5, 6, 2, 5, 6, 1, 2. Okay. So double bond here. Okay. Not really double bond. Okay. Anything else? Or is that the only one? How about 2-hexene?
I was just gonna say that 2-hexene.
2-hexene. Because in the case of 2-hexene, we'd be splitting it right here, right? If you have the hydrogen there and then the bromine there, spot, right? Okay. So that's exactly what our possibilities are. So let's talk about what would be the expectations if we get them, and then we'll talk about why. Okay, so in the case of the 2-hexene, so then we would get the carbocation added on to the 3rd carbon as we want it. And then as that happens, then that bromine will be able to interact with it. So this here is going to be our intermediate. This is going to be our final product. See, alternatively, we could have it added on to our 2nd carbon. Right? So the thing is that you're going to have both of these possibilities happening. Right? So when this happens, you're going to have a percentage that is going to be favoring one over the other. Typically, this is favored. It's a little more stable to have that cation located somewhere in the middle compared to closer towards the edge. Okay. So this guy's going to have favoring, but it's not going to be the only product. We're also going to get this as an additional product. Make sense? Okay. So in the case of 3, we basically have the formation of this guy, right? Where our cation is going to be on our 3, and it's going to bind to the 3. Oops. I gave you the answer to this part already. So what alkene should be synthesized for the 2-bromo pentane? So in that case, the 2-bromo pentane is going to have, erase. So it's going to be 1 pentene, sorry, and then 2 pentene are going to be our options. So in the case of the 1 pentene, we're going to get the cation forming on the second carbon. We're able to get the third one. This rate of the formation of it on that first carbon, the cation on the first carbon, is so slow that it almost never happens. Okay. So the first pathway is the only one that we're going to see. Okay. Let's see. So if we go with the 2 pentene, so again, we have the option of going on the second carbon, or we have the option of going on the third carbon. So in the case of this, then we will get the bromine on the second carbon. In this case, we'll get the bromine on the third carbon. So again, both of these incidents are going to occur, right? We're going to see the product being formed, even though that this is the product that we want. Right? You guys get it? No, they both will occur. So you got to think about it. So both of those. So what's going to dictate what's going to be favored is how fast the reaction is. These reactions, so this guy and this guy, are relatively close to each other, right? This one here is actually going to be favored. So you're going to have more product of this than this, okay? And it's slightly favored, but it's still going to be favored. So it's going to be like a 60-40 split. So this will be like 60, that'll be 40. Okay, so and we'll talk about that here in a minute. Okay, kind of make it a little bit clearer. What was that? No, I know. I'll give them to you afterwards, because I want you guys to pay attention rather than just read the slides. So, and also to think about it. Okay. So, well, you both notice you're like, I don't got that slide. Yeah. Okay. So in the case of so which carbon gets the hydrogen ion? Okay. So in this case, it could actually it has the ability to go technically it has the ability to go here. So this guy will become a plus, or it has the ability to go here. So this guy becomes a plus, right? So if it's a terminal, a primary carbon, it doesn't like to go on primary carbons, right? Because it takes a lot for it to find that carbon and to put something there, to put that ion there. It prefers to go internal because it helps keep a stable structure, right? So you're going to get this guy coming first before you're going to get the formation of this guy. Okay. So it likes to be in the middle. Yes. Think about how carbon is. You know, carbon likes that middle part, exercise a lot, right? Likes to be more in the middle. Again, not to say that you're not going to get that terminal, right? But you're most likely going to get the formation of the second one, right? Sorry, of the first one, right? Terminal. Or I should say, this would be the catenation. That would be the chlorine. So let me rephrase that. It's going to favor. So the bond's going to be broken here. The hydrogen is going to go here. And then the bromine is going to go there. Okay, that center. So butyl chloride is going to be the product that we're going to see the most of, where iso butyl chloride, where the chloride goes on the terminal end, is going to be less likely. Okay. So this is basically showing you the process. Okay. The electrons are going to be donated to the hydrogen. The hydrogen is going to release itself. It's going to get a plus charge. It's going to come and put its plus charge on the center carbon, giving this guy CH3 plus, right? So the charge on the center atom, the center carbon is going to be a plus. Then the chloride is going to come in and bind to that. So you're going to get the formation of your tert butyl chloride. This guy, adding it on the second one, is going to be less likely, right? Where you have a carbon added, a hydrogen being added to the center atom, and then the charge is going to be associated with the terminal. That's not going to happen. It's going to be such a slow process that, again, this guy is favored. It's going to be driven in this way. You're not going to get the formation of this. Okay, so this guy isn't going to form because this guy outcompetes it. Okay. Are you with me so far? Okay, so let's take a look at this in terms of stability, relative stability. Okay, so when it's a tertiary carbocation, it's more stable than when it's a secondary carbocation compared to a primary carbocation. Okay, basically meaning that we have a plus being added to a primary carbon, or here a plus being added to a secondary carbon. This is a hydrocarbon, this is a hydrocarbon, that's a secondary. This is a tertiary, right? Are you guys with me so far? Okay, good. Okay, and this just is kind of showing you those heat maps. It kind of helps with the explanation, right? So it decreases the concentration of positive charges on the cation by being towards the center. So it makes it a little more stable. So you have more stability happening here compared to this guy, compared to this guy, and then this guy isn't really stable. Okay. Ooh. So what affects that stability? If it becomes hyperconjugated. Hyperconjugated basically means that you're going to be adding that extra hydrogen with that plus charge on that carbon. So you have basically a positive charge, partially positive charge hydrogen interacting with a partially positive charge carbon. That's not going to be so stable, right? So as a result of that, you're going to end up getting your hydrogen to break that pi bond, and then you're going to get catenation of the carbon. Okay. Okay, so this here, the red dots, are going to represent places where hyper conjugation can occur. And again, that's going to affect our stability. Okay, so this is if the energies are going to be similar, that means that the structures are going to be similar. Okay, so the first one is an exergonic reaction. So the transitional state is going to basically resemble the reactants in the case of an exergonic reaction. So in other words, it's going to be over here. Transition states are going to be looking more like these guys over here. And then in the case of the endergonic reaction, it's going to resemble the products. So these guys over here. What was that? I'm tired. I was up way too late last night trying to get some paperwork taken care of for this week. I have my final part of my evaluation for tenure that's happening on Wednesday or Thursday. Can't remember. It's either Wednesday or Thursday. So I had to turn in some more paperwork, last parts, and so I was just working on that. Okay. So why is there a difference in rate between the two? And as we talked earlier, the one that's more stable is going to be forming faster. It's going to be favored. Where the one that's less stable, right, it's going to have a slower rate. It's going to take more energy to get to that over the hump, essentially. So it's not going to happen, right? So we don't have enough energy to get over that hump before this guy happens. Time. Okay. So in that case, the center carbon is going to be carbocation and not the primary carbon. Okay. And again, that's what this is basically showing. So carbocation is the process of what? What is the definition of carbocation? Or carbocation. So it's the process of breaking that double bond and adding the cation to that center carbon or a central carbon. Okay, so in this case, if we look at the carbocation of iso, it would be isobutene. Okay, so again, this carbon is going to form a cation, and then that means that the chlorine is going to attach to that. Okay, so this guy's going to form, this guy isn't. Again, this just basically shows you that process. So the H plus is going to be added to, in this case, the C1. And then that C1 is going to cause the bond to break. And then that center atom, actually the C2, is going to get the plus charge associated with it. So then that carbon, the secondary carbon, is going to be carbon cation. And then the Cl is going to attach to that, causing the chlorine to be on the second carbon, not on the first. And the process, this isn't going to happen, again, because of the rate of the reaction. Okay, so let's say if we have something like this. Let's see. Double bond, CH. Okay. What's going to be my product or my potential products? Think about what's going to be favored and what's not going to be favored. What's that? I said, what are going to be the products? What was that? Okay, the one's going to be broken, and we're going to get what are going to be the final products. Don't worry about the intermediate right now, but final products. What was that? We're going to have bromo by itself. Okay, so don't worry about the intermediate. Worry about the final products. You said hydrogens attach here. Okay. So you're going to have C. CH3. CH3. Hydrogen. Sorry, we're out of room. Okay. And the plus is going to be where? On this one. So then this guy would get the bromine, right? At the end for the final product. Okay. So is that going to be a major product? Or is that going to be a minor product? Well, is there going to be another product first off? Was that? Okay, so it's more stable for this to be. And the bromide here. Oops. Okay. So those are your two options, right? Are we going to form the first one? And if so, do we expect to form a lot of it or? Okay. There's going to be a little of it. Thank you. Yep, you're right. It's the same thing here too. Wait, no, 1, 2. No, that's good. Yeah, that's good. You're right. Okay. So this guy's going to be minor. And that deals with our stability, right? The one that's going to be the most stable, it's going to be around more, it's going to have more. It's going to happen faster. Okay. So what happens if we have a cyclic bond? Okay, what's going to be the products? Two. How many products are we going to get? Or what are the potential products? How many products will we get? Which one's going to be favored? Ooh. There's a methyl group there. It wasn't protruding enough. Come on. What was that? We're going to get two products. Okay. What's going to be one of them? Okay. So we're going to have one with the bromine. Okay. And then the other. Okay. So. Okay. Methyl. This is the bromine. Okay. Which one's going to be favored? Product 1 or product 2? And why? Was that? Okay. So this is going to be our major. This is going to be our minor. Okay. Good. Goodness. Okay. That's exactly what we see here, right? Okay. Again, this guy's going to be major because it's more stable to sit there and have it on that carbon that has that tertiary structure 1, 2, 3. So adding it there, it kind of bears that charge. Okay. So. Okay. So the term regional selective reaction is a reaction that forms more of one constituent isomer than the other. So these are examples of regional selective reactions. Okay, so when when we only get one product, right? So this is a more highly regional selective process, okay, than when we get one of, we're getting both products. Okay, so reaction could either be moderately regional selective, highly regional selective, or completely regional selective. Moderate basically means, oh, it does a little bit. Highly means that, yeah, you're definitely getting it skewed. This would be the highly case. Okay. And then if we have products, depending on their percentages, then that's going to determine whether it's going to be a highly or not. Okay, so this guy is not regional selective because we're getting that 50-50. Right? So nobody has an advantage, in other words. Okay. Questions, concerns, cash, Kool-Aid. Okay. So I'm gonna have us take another, and this time just a 5-minute break. So the last one where it was 50-50. So why was it 50-50? No one has an advantage, right? Because it's about the same, stability either way. Okay. It's hot compared to outside, I guess. So it's not hot to you guys. What was that? It was normal to you? You're also in a jacket. I don't know how you're doing it. You are too, huh? Yeah. No, it's okay. I'll be okay. Okay. Okay, so sometimes we have to use acids to catalyze the addition of water. So if we have water alone, we're not going to get a reaction occurring. So we need something to help catalyze that process. Okay, so if we add an acid to it, it'll actually causes the pi bond to actually be disrupted, and then it'll allow the addition of the OH and the hydrogen ion to it. Okay. So the process or the mechanism, double bond is actually going to be disrupted by the electrons moving from the double bond to the hydrogen on the acid. Okay. And so it's that hydrogen that's attached to, in this case, one of the oxides. Then it goes from that hydrogen to the oxygen. So then this process is, again, this is going to be the slow part of the reaction. So this is the rate limiting step. So then now the oxygen on the water can provide its electrons to the cation ion, the carbocation. And then the water molecule, this is going to be your intermediate. So that water molecule then it's going to take the electrons between the oxygen and the hydrogen, bring it to here. And then other water molecules are actually going to be doing exactly the same thing. It's going to transfer the electrons here. These are going to transfer the electrons here, and that's going to transfer the electrons here. And then as a result of that, we're going to end up getting the hydroxide ion added onto it. Okay. So then we'll get the formation of an alcohol, a primary or secondary or tertiary alcohol. What was that? Secondary. Okay. So we get the formation of the secondary alcohol. Okay. So we can do the same thing. Oh, and then as a result of it, we end up with the hydronium ion. Okay. So in other words, we're going to get an alcohol and the hydronium ion, secondary alcohol. Okay, so we could do the same thing with an alcohol, right? Because in the case of an alcohol, we can end up with the exact same product. Only thing, instead of getting the formation of an alcohol, now we're getting formation of, what is this? You can't start with an E. It's an ether. Oh. Yeah, it's right here. Okay, so we're going to get the formation of an ether. So if we start out with an alcohol, we get the formation of an ether. And in this case, again, we're just adding that carbon chain, the hydrocarbon attached to the O, to our, it's going to be used to basically spin up this double bond. So in this case, again, it's not going to be that terminal, it's not going to be that primary carbon. It's going to be our secondary carbon that we're going to be adding it to in this case. Okay. And then if, let's say we had something like this. Okay, we have something like this reacting with an alcohol. It's going to be the product. What was that? Okay, it's going to be an ether again, yeah. Okay, is it going to be a primary ether? It's going to be a tertiary ether? It's going to be a secondary ether. It's going to be tert, right? So it's going to be added on here, right? So the product will be okay. Questions? Okay, so the mechanism is going to be the same, okay, that we saw with the water. So in this case, the electrons from the double bond are going to donate its electrons to the hydrogen. That hydrogen is going to donate its electrons to the oxygen. We're going to end up with HSO4 minus, and then we're going to get the catenation of the that secondary carbon, then the electrons on the alcohol is going to donate its electrons to that cation. So then that alcohol is then going to have another alcohol that's going to donate its electrons to this carbon, to this hydrogen. Then it's going to donate its electrons to the oxygen here, causing this guy to form our ether. And then the product, we're going to get an ether, and we're going to get what that's called, but it's I think so in this case it would be a catenated alcohol. So, but I have to think there is a term for it. I'll have to get back to you on the term. So, catenated, yeah, catenated. Okay, so how could we say, how could the following compound be prepared using an alkene as a starting material? What are the different possibilities? Okay, what will be one of the carbons that we could use? The alkene that we can use. What was that? Yeah. Yep. You give me their names as well as their structures. You said 2, 3. Okay, so let me see. 2, 3 dimethyl. Okay. 2, and you said pentene. So that's 1, 2, 3, 4, 5. Dimethyl. 2 will be 2. This will be 3. Okay. Get it wrong. Okay. So 2, 3 dimethyl. What would be the alcohol that you're using there? Okay. And so you're saying just OH here. Let's see. 3 OH. Yeah, look at the product that you're going to make. So you're saying what would be the product? The two products. You have two possibilities here, right? So what would be the product? That would be one product. Is that what we got here? No. Okay. The other product would be that's too many. It's 1, 2, 3, 4, 5. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and pentene. Okay, so you're saying which pentene though? Because can it just be pentene? So that's 1, 2, 3. Is it 1, 2, 3, 4, 5? 1, 2, 3, 4, 5. Where would the double bond be? Okay, so 1, 2. So right here. Okay, so if it's there, so what do I need to react with? Are you sure it's going to be a pentene? Yeah. It could be an ethanol, it could be a methanol, it could be a whatever. So it just needs to pair up at the end of the day. So what I recommend that you guys do, so what is your longest carbon chain on the product? How many? So my longest carbon chain is 4. So why would I have a pentene, right? So think about your longest carbon chain. Okay, so if my longest carbon chain is a 4, then it's probably going to be a butene, right? Okay, now where? Okay, so where's that butene going to be at? So where with the double bond, where's the double bond going to be at in that butene? Next. Okay, butene. So is it going to be for us to get, because it's 1, 2, 3, 4. We want to get this attached to it. So what must this be here? Let me circle it. Okay, what is that going to be? Was it? Iso, okay, iso what? What is going to give us this structure? This is what we want at the end altogether. What am I going to react with to get the ether? An alcohol. So then iso what? How many carbons? What is 3 carbons? Propyl, right? So isopropanol, right? So then we're going to have, let's write it out, CH3, because it's easier to see. CH2, CH3, OH. Okay, isopropanol. Okay, so now I have isopropanol reacting with a butene, right? Because that's what we have here. But is it going to be 2 butene? Is that the one that we want? I guess it can be, right? So 2 butene will work. It's going to give us something. What else? What is another one? What's that? Sec butene? Are we going to have a sec butene? So this guy is 2 butene. Is there another one that can give me what I
What, 1 butene?
1 butene. Because remember, I have the option of putting it here and I have the option of putting it there. That's also going to give me what I want, right? Okay. So, and that will also work with the same isopropanol, right? Do we need a catalyst? No, we don't need a catalyst. It's just going to happen on its own. What do I need for a catalyst? Was it? I need an acid catalyst. So the only one that we've talked about so far has been, was it? Sulfuric acid. Okay, and then we know that we're going to end up with our product, right? So we'll end up with, I want to just draw my crazy structures there. So let's see if it's the edge. Oh. See there. That's 2, 3. 1, 2, 3, 4. Okay. 1, 2, 3, 4. Okay. And that's what we're going to get if we use either of these two structures. We're going to end up with the same thing. We have to use the same catalyst, and we have to use the same methanol, right? Same alcohol, sorry, not methanol, the isopropanol. Okay, is there anything else? Anyone else? Something else we can do? How many carbons is this? You got to speak up. I can't hear you. I'm old. Okay. Come on, Abby. Wake up. You need coffee like I did. I went and took a shot of my. Needed that coffee. It was killing me. Three carbons. Okay, so if there's 3 carbons, so that's 1, 2, 1, 2, 3. Where's the double bond going to be at? It doesn't matter, right? Because it's the same either way. They're going to be 1 either way we go, right? So I can put the double bond. Okay. I know my double bonds look crazy. Okay. So, and then it's going to be reacting with what? What is the alcohol that it's going to be reacting with? You said butanol. Okay. Okay, so that's 1, 2, 3. 1, 2, 3, 4. Got carried away. I'm at the race. 1, 2, 3, 4. Okay, bute. Do I do this? That's butanol. No, that won't work, right? Where should it be? Okay, so an iso. So you're saying this guy? Or are you saying, since you said an iso, it would be OH. I guess that would work. No, we need 2 of the 2, and then there. 1, 2, 3, 4. I guess that would be a turd, huh? So isobutanol. So iso means that we'd have 2 that would be in the corner. We can't have 2 in our corner. We have a sec. We got have sec butanol, which is what that is. And will that work? Because it has to be 1, 2, second carbon, OH. Well, I think that does work. So the sec butanol. Okay. And we know that the Turk wouldn't work. Right? Okay, so those are our 3 options. So 1, 2, 3 that are going to give us our product. So we have 3 products, 3 ways of getting to the same target, right? No, you don't have to use the longest chain. I mean, because both ways are going to give you the same product, right? So you could use something that has a short chain, well, because all you're doing is kind of switching out the chains. If this guy is long, then this guy has to be short. If this guy is short, this guy has to be long, right? Yeah, no, maybe. Yeah, well, in this case, yes, it does, because you have 3 here, 4 here, right? So we could either do it this way where these guys, the alcohol is coming on this side, or we can do it the other way where the alcohol is part of this side. This side here. Nobody's colorblind, right? So much trouble when my 1A start 12A. I have a student that's colorblind. So far, on my online classes, every semester I've had somebody who's colorblind. Makes things very difficult. Yeah, they do. And so I'm trying to prep my diagrams and stuff because I like using color, if you can't tell, right? Because it helps me see things. So then I have to think about, okay, I use hash lines or, you know, which is not easy to draw. So I need to get a system. I should tell Canvas, not Canvas, Zoom, you guys need more options in your annotation report. Okay, so you guys see how this works? Practice, yeah. Okay. Okay, so when we talk about, in this case, oops, I guess I should kind of clear it. So we talked about the major and the minor, right? So here, we have a major and a minor product, right? Now, although we end up getting a surprise, right? Because the double bond is right here, right? But we get the addition of a bond here and a bond here. Okay. Why is that? It's based upon stability of the product, right? So this guy would be this one. In this case, this one here would be a minor, right? So normally we'd assume that it would go here at this point and here. But instead, we get here, right? Okay, now this has to do with rearrangement. Okay, we haven't talked about why this happens, but I'm going to show you here. Okay, so the same thing is going to happen in this case. Okay, so here's our product. So basically what we've done, we're going to get a switch that happens. Okay. So then our major product is going to be this guy. Okay. The 2-chloro-2,3-dimethylbutane is our major product compared to the 3-chloro-2,2-dimethylbutane. Yes. Yeah, so rearrangement, meaning that here that methyl group is going to rearrange, move itself onto the other side. So the methyl group is going to come over here, and then the chlorine is going to go over here. Okay, say chlorine is here, methyl group is here. They switch partners. So I'm going to show you. Okay. Yes, it happens in reactions. This is why chemistry is fun, right? Because you have more stuff to remember that could happen, right? So because these guys are, it has to do with the fact that these guys are, here, I'll just show you. Okay, so this guy here, so this is our secondary, right? Okay, so again, the double bond is going to be providing the electrons for the hydrogen. The hydrogen is then going to provide the electrons for the bromine. So then the bromine is going to have a negative charge. The hydrogen is going to have a positive charge, and it's going to result in a positive charge being placed here, right? So now what happens is that we have a 1,2 hydride shift. So this guy now moves here, which allows this guy to have a plus charge. Okay, that's what we get here. Now, if we don't have our hydride shift, so if we take a look at this guy gets the hydrogen, this guy gets the plus charge. If we don't have this shift occur, right, then we end up with this product, which is our minor product. So instead, we have that 1,2 hydride shift. So that means that we now have a cation on this carbon here, second carbon. Okay. And then the bromine will attach itself there. Okay, sure. So the electrons are going to start off on the double bond. Double bond transfers his electrons to the hydrogen. The hydrogen transfers those electrons to bromine. So then now the bromine has a negative charge. Right? The hydrogen is then going to attach itself to that carbon right here, causing this guy to be carbon cation. So then that carbon cation now is going to have a shift occur. So this hydrogen is going to shift over to that carbon. Okay. And then it causes this carbon to be cation right here. Now, the reason it does this is because by it's making this shift, it makes that charge a little more stable. Okay. So we have stability associated with that charge because it's varying in a sense. Okay. So now this charge is now able to be, you're able to add the bromine to it. Yeah, the hydrogen shifts over. Okay, now this also could happen with methyl groups. If there's a methyl group here, which is what I'm going to show you next, the same thing is going to happen. Because it's looking for ways to try to make something a little more stable, to make that intermediate more stable. And so it takes that shift to do that. How's it going? Next door. Yep. Yep. Okay. Do you guys see? You guys are at home. Do you guys see that? Are you there? Yes. Yes. Yes, because it is a very slow reaction. So it has enough time to do that shift, right? Okay, or yeah.
Are we gonna have like a test on that or?
Yeah, yeah, you're gonna have a test on it. But it's just because, again, it has to be primed. First off, it has to be primed. Okay. It has to be initiated by this guy, right? So that first off, let's say double bond has to first provide its electrons, right? So by its providing its electrons, it causes this intermediate to occur, right? Now we know that this guy here has some stability associated with it, right? But it would be better if we had the plus charge here, right? Because we know if we look at relative stability, if the plus charge is here, it's more stable. Now, it has time to sit there and make that change. So it's going to try to find a spot where it's stable. Remember, electrons are always moving. Because they're moving, they're going to be shifting to allow for that stability. Okay. And so you have to think about it is, it's like, okay, so you're in bed, right? Okay. Now let's assume when you're uncomfortable, do you shift? Right? So until you find a point that's more stable for you, more comfortable, right? So essentially, you've got to look at it like that because the electrons are going to be moving till they find a stable structure, right? Then once they find that stable structure, then this guy is an opportunist and it's going to jump in and, okay, you're at that structure that I want you at. Let me come in and attach now. Exactly. Well, it's not because the hydrogen is not comfortable where it's at. Hydrogen is fine where it's at, but it's this carbon, right? He's not comfortable. And so since the electrons are moving around, it's easier for it to sit there. Okay, so those electrons are moving around. If we move those electrons here, then I can take advantage of this hydrogen. I can get this hydrogen over here to help me be stable. Right? And it has to do with this, the fact that this guy has, you know, it has 3 attachment, it's varying something. So it's able to give up something to help the other guy gets a little more stable. Yeah, it gives up, well, it gives up 1 attachment to, and so to allow this guy to become a little more stable, right? And so overall, the molecule as a whole becomes stable. Okay. It'll start, I'm not gonna say it's gonna start making sense because it doesn't click until afterwards. And still, there are some days that I'm like, okay, I have to look at the card because I couldn't remember which one's gonna shift now, okay? So it's just gonna take some memorization and then understanding that you're looking to try to find stability, right? It's all about stability at the end of the day. Which one is gonna be higher in energy? This guy is higher in energy, so it's gonna try to find a way of making it lower in energy. The way that you make it lower in energy is by having that shift. So this guy is gonna shift over and attach here, right? So remember, I told you the same thing is gonna happen in the case with a methyl group, right? Yes, and take your steps. Yeah. That's why we have to pay attention to those intermediates, right? Because in a sense, you're going to have 2 products, right? You're going to have your minor product, which is going to happen by this. And again, the reason why this happens, this is a slow reaction. This is a very slow reaction for this to sit there happen, right? Which is like, this part is a slow reaction. This is a fast reaction. Now, the problem is that it takes so long for this to get here. It has the ability to sit there and switch this over, right? So then you have more product, and this guy's a more stable product than this guy itself. So yeah, it'll attach here if it has to, but it prefers this one because it's a better attachment. It's a more stable attachment. Okay, so if I had, let's say, instead of methyl groups here, if I had an ethyl group here, what do you think it's going to attack? What's going to be rearranged? If these 2 were methyls and that was an ethyl, would it be the ethyl or would it be the methyls? What was it? One of the methyl groups would rearrange. Okay. So if these were all 3 ethyls, then well, it would be one of the ethyl groups would be able to switch rearrange. Right? Are you? Okay, I'll give you guys more homework on that. Okay. Okay. So let's see. Let's see if I can get you a problem to kind of help us through this. Okay, so I like the problems. They work backwards a lot. Talked about that. Talked about that. Where is it? Now we're on the leftover rearrangements. So let's try this problem. Let's see. Okay. Let's see. Talk about methyl rearrangements. Starting surprise. Okay, here we go. Okay. So we get the methyl rearrangements clear. Okay. So here, if we go ahead and look at this one. Now, this guy isn't going to rearrange. So what is the distinction between this guy and this guy? I shouldn't say this guy and this guy. What is the distinction between the 3,3-dimethyl 1-butene compared to 1, 2, 4, 5? So the 1, 2, 4, I'll say the 4-methyl 1-butene, or no, pentene. There's what? There's no tertiary carbon. There's no tertiary carbon here either. Right? What was that? Okay, what do you mean by that? What do you mean by more carbons? There are more carbons, but you know, we have. There we go. Okay, so here the double bond is right next to the bond where we're going to be hijacking stuff from, right? So you can't hijack something from. Okay, so you're here. You have your neighbor right next door, right? So you can take stuff from your neighbor without a lot of hassle. But trying to take something from down the block and get it to your house is going to be a lot more work, right? So it's easier for you to sit there and borrow that or rearrange that from your neighbor compared to somewhere else. And that's the distinction. So if we take a look here, the double bond is at the 1, right? Okay. The secondary, the secondary carbon is located 1, 2 over, not just 1 over, right? Where here, in the other example, come on, okay, here it's located only 1 over. It does, yeah. Because it's hard to really, it's hard to sit there and take for something that's further away. It's not like an easy grab where, because look, you're just trying to rearrange it, right? If you have to sit there and let me pull you over one and then pull you over another, that's a lot more energy, right? And it's all about energy. Okay, so in this case, the only thing that we're going to have is going to be that first product. So that's going to be a major product. We're not going to get any of this. Okay. So we're not going to get any rearrangements because it's too far over to allow for that rearrangement. Okay. And the other thing is we want to pay attention to, you notice it's not hijacking the hydrogen off of here, right? Why isn't it doing that? Why isn't it hijacking the hydrogen off of this guy? Off of. Okay. So because this guy had those, it has those two other, let's say go back. It has those two other methyl groups in this case 3 methyl groups, right? It gives it more stability. This guy would have stability. If it takes this hydrogen from this carbon, right, it's not going to do any good. It's going to mess up with the stability of the structure. So you're trading one bad position for another bad position. Do you guys get that? Okay, good. So let's see. Practice. So which of the following carbonation would you expect to be rearranged? Then I think this is going to be a good stopping point. I just feel like we're going so many different places. We get a little bit of nomenclature and then we start doing these crazy reactions. Okay, you said B and E. Okay. Okay, explain. Okay, so it probably already got it from the methyl group. Okay. Right next door to the methyl. Okay. 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 Yeah. So the correct answers are B and E. And you're exactly right. It's going to be pulling from here. Does it need it? Like you were suggesting, or actually it's too far away to get it. And then C, it's a tertiary carbon already. Doesn't need to rearrange because it's already stable. D, already stable. And then F. So this is a secondary carbon, so it doesn't need to rearrange. Carbocation. Okay, we found our alchemist in the group. Okay. Okay, so let's go ahead and stop here today, and we'll pick up on boron. So boron is BH3. Its common name, boron. We'll pick up a boron on Monday, next Monday. Yeah.